Sorry for forgetting to click record during the class review. So this time I'm going to go a little bit quicker than what we did in the class by starting with the chapter 5. So in chapter 5, basically we talk a lot about the tension test, compression test, shear test, flexural test, and fatigue test. And for the tension test, most of the time we test for the rubber, steel, and iron, cast iron, in order to get the mechanical properties such as the ultimate strain, yielding strain, percentage elongation, and Young modulus. And for the second one, it's going to be the compression test. We test on concrete, grid, wood, parallel, and the perpendicular to the grain. For the shear test, we test for double shear, single shear. For double shear, we test on metallic material such as brass, coppers, aluminium, and also we cast iron. But for the single shear in the lab, we test just only for the wood that parallel to the grain only. Next one is going to be the flexural test that we considers on the wood, cast iron, and iron only. And lastly is going to be the fatigue test that we test on the aluminium and to see the behavior of it. So to answer the question one, which type of force metallic material usually support and test? Of course, it's going to be the tension test. Moving to the second question, why is concrete is not commonly tested using direct tensile method, and we're going to see it in lectures later, and then we're going to go through one by one. According to the TAS, for the hot roll using the code of 1227, and for the cold form steel using the TAS code of 1228, you can see that we consider, like for the normal testing, we consider a lot of things such as proportional limits, yielding stress, ultimate stress, fracture stress, percentage of elongation, percentage of area reduction, modulus of elasticity, modulus of resilience, and the modulus of toughness, right? These are all the mechanical properties that we consider for design and observe the behavior of the material. But for the TAS, we consider just only the red highlight text over here, which are yielding stress, ultimate stress, percentage of elongation, and modulus of elasticity only. Therefore, in the examination, I may ask you, what are the important mechanical properties of material obtained from tension test? So I may trick you by putting just only one tensile test and put proportional limit, fracture stress, percent of area reductions, and modulus of resilience. Then you need to pick the one from TAS, which is the yielding stress. Okay. For the second one that I would like to focus is going to be the TS 1227 over here. And I want you to be able to understand what is the classification in such as the text that indicate the ultimate strength. For example, like SS 400, which means the SS is steel grade and then 400 is going to be the strength of the steel that indicate the ultimate strength. For example, in the table, they specify it as the tensile strength with the unit of Newton per square millimeters or megapascal. For example, if it is SS 400, it's supposed to have the minimum tensile strength not lower than 400 megapascal. And for the thickness below 16 millimeters, it's supposed to have the thickness, it's supposed to have the yielding strength not less than 245, and for the thickness that larger than 16 millimeters, it's supposed to have the yielding strength not less than 235. Okay, next one. This one we already talked about it. If we talk about the metallic material, we normally test for the tensile test because of testing compression test of the metallic materials sometimes can happen on the buckling. Okay, so buckling can be happen, and if we would like to avoid it, we need to make the sample to be in a really short sample, but it requires a really high resolutions of the testing machines, and it's really expensive compared to the tensile test. So that's why it most of the time controlled by the tensile test. But for the brittle materials such as concrete and brick, normally it's used to support the compression force. That's why we test for the compression test, okay, to observe the compression strength. Also, this one, I already mentioned in the class that for the timbers, it has a really good tensile strength. If we rank the strength from 1 to 3, which one provide the best? It's supposed to be the tensile stress. And the second one is supposed to be the compression stress. And last one is going to be the shear stress. Okay, so in the examination, if I ask you to put this in order, you guys need to be able to rank it like this by providing tensile stress is the best one, and the middle one is compression, and the last one going to be the shear test. So that's why in the timbers, we rarely test for the tensile, but we test for compression and shear test according to the material behaviors and according to the failure mechanism of it. Move to the second one, move to the next slides. We see that concrete is going to test by using compression force. Okay, and to test the tensile force of the concrete, we cannot test it like the figures on the left, which is the tensile strength of the steel. Because of we cannot grip the sample as in the steel like this. If we grip the concrete sample like this, at the head and the bottom of it is going to break. Okay, and we cannot grip or we cannot hold the sample. So to get the tensile test from the concrete, we test in a test called slitting tensile test, which is going to lay the cylindrical sample like this on the figure on the right, and then we're going to apply the uniform load to the sample horizontally like this, and then the force is going to press up, the hydraulic is going to press up, and then the force is going to transverse into the concrete like this, and then the concrete is going to react by the tensile force. So because of the concrete, it's brittle and difficult to grip. So that's why we're not gonna test by direct tensile compared to the steel. Okay, so this is the answers. And for the question number 3, which method is commonly used to substitute to determine the strength of the concrete? Of course, the one that we just discussed is the splitting tensile test. Okay, this one is the correct answers. And for the fourth one, when the crack occurs at the middle, it caused by the tensile stress. Okay, so this is the answers. For the specimens, we can see that normally at the end of each specimen, it provides a larger section just because to transfer the stress uniformly without failing at the end of the sample. We would like it to fail at the gauge length more than the end of the sample. And we have like many type of the end, such as the shoulder end, threaded end, and the pit end. And if we answer the question over here, question 5, why must the center tension test have the end are larger than the center of the portion? The answer is supposed to be the second one, right? Which occurs in the middle. Okay, we would like the sample to fall at the middle. And question number 6, which of the following specimen characteristics should not be used in the tension test? If you look at the figures over here, you can see that we have 4 defects of the sample that we don't want to use in testing. For example, is the first one, the center line of the end of the sample is at the middle over here, but the center of the gauge length is off the grid to the top. So this produces the eccentricity length, which when we pull it, it's going to provide some eccentricity length, and the stress is going to be larger than what we want it to be. Okay, so this one is not good practice, or some kind of defect like this, not uniformly aligned, and we have two-side reduction of the section, or maybe not symmetrical, and last one is going to have some defects at the end of the sample. So in the question number 6 over here, we need to pick the misaligned axis as the eccentricity. Okay, and number 7, how does an excessively high stress test speed affect the result of the tension test? We can just easily pick that the measure strength is higher and the ductility is lower than the actual. It feels like you pulling the straw. If you have like the plastic straw, if you pull it slowly, the straw is going to elongate slowly, okay, according to the slow rate. But if you rapidly pull out the straw, like in one time, like just rapidly pull the straw, what happens is the straw going to resist a really high force. But the thing is, we cannot see the plastic behavior of the straw. It's going to break into two parts immediately. Okay, so that's why when we test at really high speed, the measure strength is supposed to be higher than normal, and the ductility is going to be lower than actual because it has no time to yield. You just pick the top one, and again, I would like to repeat this in the testing lab, we use a lot UTM machine. UTM come from Universal Testing Machine, and we test for tensile, compressive strength, shear, and flexural. And this one, if I ask in the examination, you need to pick a proper testing according to the questions. Then I want you to go back and revise on this, on the load controlling test. If we talk about load controlling test and displacement controlling test, so in short, load controlling test is good for brittle material such as cast iron. Okay, it's one of the good example, or concrete. And for the displacement controlling test, but concrete is good for just only bending. Okay, concrete is good for only bending. But for the displacement controlling test, you can get any behaviors of the material. You can adjust just only the strength to be smaller for the brittle material, and then you can record any behaviors of the forces according to the material behaviors. But for the load controlling test, in example like this, for the ductile material, such as steel, like this. Okay. If you use load controlling test, you're going to set what is the rate of the force. For example, I'm going to record it every 10 Newton. Okay, just for example, if I record it every 10 Newton, increment means increase. So when it increase every 10 Newton, it's going to record the strain for me at one point. So when it go up 10 Newton, I'm going to record one strain. But during the plastic region over here, the load is not gonna increase. Okay, so the machine is not gonna record the force during this stage, which means our sample deformed, but we have no data about it. So that's why it's not really good for that kind of material. But if the sample is retold and behave nearly like this, it's okay. So whatever is the rate that you put it, you can just record the strength immediately like this. Okay. So load controlling test is good for brittle material, and displacement controlling test is good for any material. Okay. If it is brittle material for displacement controlling test, you can just adjust the strain to be smaller for recording the force. That's it. The failure from tensile tests, we have a lot of failures. For example, like flat granulars, cup cone, partial cup cone, and star fractures. Look at the question. A cup cone failure is a characteristic of which type of material? If you remember, you test the steel from F1. After you pull it, you can see that there are some area reduction and then produce the angle of 45 degree to your sample. Okay. That's one come from the shearing stress to the grain, which make the sample to shape from the bigger area to the smaller area and produce the angle of area at about 45 degree. And if you observe it from the lab for the tensile test, you can see that for the cast iron sample, you're going to produce a 90-degree failure as these figures. And we're going to discuss about it later. But over here, if it is 90 degree like this, of figure A, this one is for the brittle material, and if it shows some reduction of the area over here, it's going to be a ductile material. So just click on ductile, and that's the answers. The failure of ductile steel under tension is primarily caused by which type of stress? As we have discussed, for the tensile stress, according to the tension, this one is going to fail by the shear stress with the angle of 45 degree. Move on to the second one, to the question 10. Number 10. The failure of cast iron under tension result in a fractured plane at approximately what angle of longitudinal? For the cast iron is the brittle material. So when it fails, it's going to fail at 90 degrees, as what we have just discussed. Next is what is primary advantage of displacement controlling test? Any material for all regions, including plastic zone. Okay. 12. If eccentricity occurs in tension test, how would it affect the measure strength? So we discussed already previously, the strength is going to be higher than reality. Okay. But the actual strength, this one is supposed to show strength, it's lower than reality. Okay. So to change this a bit. For the test fit, we discussed already. Okay, for the eccentricity, it causes to have higher stress because of this term. It's going to have an extra uh, stress caused by the moment and the eccentricity length. Okay. The failure of the steel and cast iron subject to the tension load, we have two types of it as ductile, subjected to tension, going to produce 45-degree failure surface, and it caused by the shear stress. And for the brittle material such as cast iron subjected to tension, it's going to fail at 90 degree and it failed by the tension stress. Okay, some example. And then I forgot to answer this here. For the concrete, we normally test for the compression. Basic answers. And then move on to the static compression. Static compression, we talk a lot about concrete, brick, and wood. And let's have a good start with the mechanical property, such as proportionally made yielding compressive stress, ultimate compressive stress, and modulus of elasticity, and also the modulus of resilience. Again, the red highlight is the requirement from TAS, which you guys need to know, and then I'm going to trick you guys in the exam that which one is going to be the most important CE field. So you may need, according to the TAS, you may need to pick one out of these three. For the question number 14, how do stress and curve of cast iron compared in the linear elastic region under compression versus tension? So they would like us to observe the linear line over here according to the offset plane. You can see that the behavior are similar. So just click similar to each other. Question number 15. In concrete compressive test, why does slope of stress strain curve initially increase? Okay, just only a simple point. Because of concrete, it's has some void in it. Okay, concrete has some air void in it. That's why when we press it like this, the void in the concrete is going to close. Okay, the air in the concrete is going to close. When it closes, what happens? It's going to rapidly increase in stress. Okay, that's why in stress center of the concrete at the initial state of the section diagram is going to increase rapidly, and then it's going to slow down, behave as the ductile material. For the question number 16, a critical problem to monitors when testing long specimen, we discussed already, just only the buckling. Okay. For example, like the steel over here. Height of the steel is lower than the largest one. It's going to be really hard to make it bend as a normal sample of the steel. So the critical problem to monitors during the testing, it's just only one thing that you need to consider from question 16 is the buckling. As you may know, if you would like to get the compression steel properties, you need to make the sample to be really small, okay? And then need a really high accuracy of the testing machine. That's why we can prevent the buckling from the steel. But if we test the steel as we test at the lab for the buckling of the steel, you can see that we test in various length of the steel, and then when it failed by buckling according to the weakest axis of it. So the thing that we need to consider is just only the buckling. What is the effects of the friction between loading head and compression in the specimen? So the effects of friction over here is it going to cause your sample, okay, to fail faster than what it should be, which means the measured strength is going to be lower than the actual if you don't cap it carefully, okay. But in the lab, I think people cap it using capping. But in the past, they used plasters and sulfur, but this one take time to prepare. That's why capping is the most famous one right now to use it to prevent from damaging or avoiding the friction on the surface of the compression test of the concrete. And then if they ask, so how to prevent the buckling of the section? So you guys need to have the height of the sample supposed to be in between or smaller than 8 to 10 of its diameters or at least section. So it's going to be 8 to 10 times according to the quiz. And for the question 20, concrete cylinders diameter is supposed to be at least how many times larger than the maximum aggregate? So this one we can answer easily. It's supposed to be 3 times larger than the aggregate size. Okay, so this aggregate size, normally we have the largest of about like 2 inch. And if 1 inch equal to 2.5 centimeters, if it is 3 times of 2 inch, it's supposed to be 6 inch. We know that 6 inch equal to 1 inch equal to 2.5. 6 multiplied by 2.5, it's approximately 15 centimeters. Okay, and the depth of the cylinders normally it's going to be 2 times of the diameters. That's why we have the concrete sample of 150 in diameters and the depth of 300 millimeters. And again, I would like you to go back to check on this. Okay, so I'm going to ask you what are the laboratory tests using the this UTM machine. Okay, so you may need to go back and revise it on your laboratory report. This one just click 3 times. 21 fractions from friction test cast iron usually occur in what angle to vertical axis? So for the cast iron, it's 45 degrees because it's a homogeneous material. Okay, so it's a hot rolled steel, which means when they manufacture it, they're going to manufacture it by using heat, and then it come as the homogeneous shape like this. But for the concrete, it's going to be a different story because we're going to mix coarse aggregate with the sands, or we call it fine aggregate with the cement plus waters and add the admixtures. And sometimes it's not gonna fail like a homogeneous material as cast iron or aluminum on top. Sometimes it fail by the mortar, and sometimes it fail by the aggregate itself. So basically, and normally it fail about 50 to 60 degree according to the vertical line like this. So this one we can just answer it as 45, and for the concrete is 50 to 60. And why is the fractures of concrete not exactly 45 degree? You can just pick over here because concrete is not a homogeneous material, which contain of coarse aggregate, fine aggregate, cement, and waters. For a shear cone failures, okay, if you look at the failures, you have sample of mortar and cylindrical shape of the concrete. For the shear cone of the mortar, it basically failed by the shear stress. And for the shear plane failure like this, it failed by the shear stress. Normally occurs in the cylindrical specimen of cast iron or concrete. and it failed about like 45 to for again for cast iron it's going to fail at about like 45, but for the concrete it's going to fail about like 50 to 60. And last one is the failure caused by shear stress plus tension stress, which create a shear cone with vertical crack like this. Okay, but this one is rarely occurs. Normally, it's going to occur like a hourglass, which caused by the shear stress as the first one. Even though it's in a cylindrical sample of the concrete, most of the time it's going to fail like this. Okay, this one we discussed already. So we can just pick over here, concrete mortars. And for the question 25, we're going to talk things on the wood. If we press the wood perpendicular to the grain, the thing that happened is it failures match with this one. We call it crushing. The crushing is going to deform, or we call it settle in a small depth over here. And then it loses its strength. So this one we call it crushing failures. And if we test it parallel to the grain, this one just pick crushing. And if we press it parallel to the grain, the thing that can be happen is two mode. The first one is going to be the shearing can be happen, and then the next one is going to be the splitting tensile test over here. All right, so just buckling of fibers over here. And for the equation of the double shear, as you may know, so if we test for the coppers, aluminiums, and cast iron, we're going to test it by using double shear, which we attach the material at the middle, and then we have the grip at both sides, and then we trying to apply the force at the middle like this. Okay, when we apply the force over here, the area resistance of the sample is going to be 2 times, okay, compared to the single shear in the wood or in the timbers. So the equation over here, if it divided by 2 area, which means this one is the double shear, and for the single shear, again, we test for the timbers parallel to the grain, which has the equation of just only force divided by area. But for the double shear, it's going to be force divided by 2 times of the area, because there are 2 resistant surface over here. This one is area number 1, and on the right it's going to be area number 2. And then for the direct shear test, for the double shear, most of the time we test for the coppers, aluminum, cast iron, and for the our CE field is the drilling augers over here, which are going to apply the torsional force to the ground in order to push the soil or getting the soil out in order to cast a concrete pile like this. So to estimate the torsional shear stress or shear force, torsional shear force, we need to understand that our sample that's subject to the torsional force is going to create something called pure shear. Pure shear means when you squeeze or when you rotate by using the torsional force, there will be some shear force occurs on the surface only. If we compare it to like the normal force, if we apply the compression force to the sample, there will be some tension force that occur to the sample too, which means it's not only the compression force, but it's plus with tensile force at the size of the material. But for the torsional shear, when we apply it, it's going to produce just only the pure shear, okay, which the inside material going to experience the pure shear only. That's why this one we need to pick pure shear. Which one? This one is torsion, and this one is going to be the pure shear. Question 29. And question number 30 is going to be the limitation. Sorry, for the question 30 is going to be the limitation of the shear test. So we're going to discuss about this later. Let's go back to see the testing over here. So in the examination, I'm going to ask you to convert from degree to radian, or maybe from radian to degree, in order to find the angle of twist, in order to find the torsional shear stress, and in order to find the torsional shear strain over here. So the polar moment of inertia over here, I'm not gonna provide you the instant value. You guys need to go back to your mechanics of material from City Chai's video clips, and then learn from it again how you get the polar moment of inertia in order to be able to get these parameters for the calculation in the examination. So this one is a big note. And these are the shear strain diagram. I already explained this a lot previously, so I'm going to skip this. And this is when the question 30 come, is when we test for the direct shear test, we can see that we cannot draw the thing called shear modulus, or we cannot find the thing called shear modulus of elasticity, because we cannot find shear stress and shear strain from that direct shear test, okay, compared to torsional testing. That's why you cannot find shearing modulus of elasticity. That's just only one bad point out of direct shear test. Okay, so just click here. Then why is the torsional test not used for the shear strength of a brittle material? Is because of it cannot be measured directly to get shear strength from the torsional stress, from the torsional test. When we try to rotate the brittle material, okay, or we try to twist the brittle material, the tensile stress is going to occur internally, and then it's going to produce the angle at 45 degree. So if we talk about shear strength, it's not shear strength because it failed by the tensile stress. Okay, so that's why this one we need to pick number one. Material is going to fail under the tensile stress at 45 degree, not failed by the shear strength. And lastly, if we would like to get the best output out of the torsion test, we're supposed to test for the sample with the hollow section with the thin wall thickness, or it's going to have a really thin of the thickness in order to avoid the shear resistance inside of the sample. Okay, so when we apply the torque like this T, so we don't want the internal to provide some friction, and if the shell or the outside diameter is small enough, so we can just make sure the shear strength directly from the tensile test of the ductile material. Okay, this one you need to go back and look at it, and this is some material that we tested a lot. Okay, this is what I just explained. Inside is hollow, and then we can measure the torque or the torsional force directly. Okay, so just pick the thin wall hollow cylinders. And for the question 33, the torsional failures of the ductile steel result in a fracture plane of which one? So for the ductile material under torsion, and it covers the failure plane of 90 degree and failed by the shear stress. So normally students just confuse between the material under torsion and material under tension. Please divide it carefully. For torsion of ductile material, it produces 90-degree failures and failed by shear stress. And for the brittle material under torsion, it's going to produce 45-degree failure surface and caused by the tensile stress. So if we pick from the quiz over here, the best answer is supposed to be perpendicular to the surface, 90 degree, and torsional failure is supposed to be 45. Okay, and one more point to note is the material properties of the cast iron. For the cast iron, we give it number one strength of the compressive strength, and the second one is going to be the shear strength, and the third one is going to be the tensile strength. So if in the examination I ask you to rank the strength of cast iron in order. So you need to use this order in order to rank the strength between these three. Because this one is already been told, for the tensile strength, it can resist up to only 240. Compared to the steel, it can reach up to 713 megapascal. And if you compare shear strength, almost similar. For the compression strength, we are found it is. And then cast iron have the lowest for use. It's supposed to be tensile strength. Okay, the weakest one of the weakest one of the cast iron. And for the question 36, we're going to talking about bending. For static bending tests, we talk things about two of the mechanical properties, such as the modulus of elasticities. But in flexural, in bending tests, we call it flexural modulus of elasticity and modulus of ruptures, which indicate the stress or the resistant force of the bending. According to this, um, I would like you to understand the different type between 3-point loading and 4-point loading tests. Okay, for the 3-point loading test, its characteristic is to have the maximum shear at the middle of the span with the maximum at the middle of the span. Okay, so everything maximum going to be at the middle of the sample. But for the 4-point loading, it's going to provide a really good loading behaviors, which is better for theoretical proof of the equation, which has no shear center and going to provide just only bending moment at the center of the sample and then move the shear to the side. But the disadvantage of this is really hard to set up. So that's why in our lab, we're going to use just only 3-point loading. For the 3-point loading, we have just only two nodes that you need to be able to do it or remember it. For example, like the first one, Vmax is going to be the plus minus of the reaction, which means if you apply force P, the reaction is going to be P over 2 for both sides. If we sum it in sigma Fy equal to 0. And for the maximum moment, we can calculate from the internal load. If we internal moment by cutting the section into half, it's going to be the distance is L divided by 2 multiplied with the reaction force of the P over 2. We're going to get the maximum moment equal to PL over 4. Okay. And the critical point or the main equation that we're going to use for bending is going to be from here. Okay, sigma equal to MC over I. So this one is going to be the main equation that we're going to use and that we're going to derive for the testing in the labs. Okay, so I already discussed about this in the class that you guys must be able to derive this equation of the rectangular section. For example, we know that stress equal to MC over I, and then the maximum moment of the 3-point loading, okay, 3-point loading test is going to be PL over 4, because all of the material that we test in our lab, we use 3-point loading test as the reference. And then we know that the C over here is going to be this half of the depth of the sample. So it's going to be D over 2 if D is the depth of the sample. C is going to be the distance, half distance over here. So it's going to be C. And moment of inertia is going to be I. Just like a simple moment of inertia of the rectangular section is 1 over 12 BD power 3. And we can just substitute everything together, and then we're going to get the maximum stress equal to 3 PL over 4 BD. But in the examination, I may change it to 3B, 2D, or maybe some question. I may like to put it as 2L. So please carefully substitute it in this main equation. And another one is going to be the maximum shears of the rectangular section. We can just use this equation from mechanics of material as 1.5 Vmax over area. And next one, because we use 3-point loading, the maximum deflection of the sample can be found easily equal to PL power 3 over 48 EI. So this equation, I'm going to use it in order to let you find the parameters that I consider. For example, if I would like to find E, I may tell you what is B max, what is P, what is L, what is I, and then you can just like relocate the parameters in order to find E for me. Okay, or maybe sometimes I would like to find P, you can just move everything to the side in order to find P. Okay. And if we answer the questions here, bending stress often used to determine which property of the brittle material? Of course, the tensile strength. Okay, because of compressive strength, we test it as the normal one. But for the tensile test, we cannot like pull it. So that's why we use this bending test, static bending test, as a representative of the tensile strength. And then the modulus rupture referred to the flexural stress at fracture. So the maximum resistance capacity of the tensile stress of the section. And what else? The advantage of 4-point loading compared to 3-point loading, it's just a pure bending at the centers without shear. And 39, what occurs when the plastic hinge form in a ductile steel beam? Okay, we're going to discuss about this later. All right, so if we move to plastic hinge, this plastic hinge occurs. How can we know that the plastic hinge occurs? So we can just observe it easily when you apply a really small force and it deform a lot. It provides a really high deformation. So when you apply like this, it deform or it yield a lot. Okay, when it yield a lot in a ductile material, that point we call it plastic hinge, which means its deflection increase rapidly by applying just only a minimal load increment. Okay, this is its definition. And if we go back to here, so to avoid shear failures, as the question 40 asked, what are the span to depth ratio that we need to consider? So it's supposed to be larger than L over D. Okay, so it's in between 6 to 12. Okay, if it is smaller than 6 to 12, the thing that happens is it's going to create a shear failure at the neutral axis. If you observe it from the lab, we have one is really long and another one is really short. So the long one is going to be this one, okay, because we would like to avoid the shear failures. But the shorter one is we're going to test it to see the behavior of the shear failures. And to avoid the lateral buckling, we need to have the B over D supposed to be smaller than 15 over here. So it's just only the cross section of it, B over D. So this one, to avoid lateral buckling, this one is to be not less than 6 to 12. For the 42, the local buckling typically occurs in the Y flank. So this one from the experimental study in here. Okay, so I'm gonna skip this. And comparing I-beam to the rectangular beam of equal area, which one is true? I section. Okay, so that's why I-beam has a higher failure strength. And for the horizontal shears, failures occur in the timber beam. Okay, so we're going to observe it like this. Okay, lately we have been here. So this one, just mark it. When we test a static bending to the cast iron, you can see that the TA want you to tie at the end of the cast iron sample in order to avoid the, in order to just because the safety concern, because when it breaks, it's going to break by the tensile force at the bottom. So when you compress the force like this, on top is going to experience the compression, but at the bottom is going to experience the tensile force. And when it fails, it's going to fail immediately, which means it's going to feel like the explosion. It's going to break into two pieces without telling you a warning message. Okay, so that's why we need to tie it first in order to be safe during the testing. And for the failure of the timber beam, I think you tested already. You're going to see that we have two length of the sample. The sample number one, most of the time fail by tension, but sometimes it can occur by failing in compression. And the shorter one is going to fail by the horizontal shear. And the horizontal shear is going to fail at the neutral axis, which means almost at the middle of the sample. Okay, so if I would like to ask you for the horizontal shear of the timber beam, you need to tell the location that it's at the neutral axis. And for the support, and for the question 45, how does flexible strength of a large beam compare to the small one? This one is just like a general one. When the beam is larger, it's going to have a higher defect chance, which means the larger the beam is, the lower the strength can be happen. Okay, compared to the smaller specimens. Okay, that's about it for the static bending. And for bridge, we call it as the unloading to the bridge, which means when a vehicle is on a bridge, we call it loading. When it passes a bridge, it's unloading. So the number of the vehicle that pass through, we call it number of cycle. Okay. We call it number of cycle. So number of cycle, it's normally write as n, loading and unloading, and then it's going to cause this values. Okay, and next one that I would like you to remember is this equation, a few short equation. You can see that the mean stress is really easy to calculate it. Mean stress means the average stress. For example, if you load the sample to the maximum force of 10, and then the minimum force of unloading to minus 2, so this one is going to be 10 plus minus 2 is going to be 10 minus 2 divided by 2. The average is going to be 4, right? So it's going to be 8 divided by 2 is going to be 4. The stress amplitude is going to be 10 minus the minimum, minus is going to be plus. So this one is going to be 6 megapascal. Okay, and the stress range is going to be determined by stress maximum minus the stress minimum. And you can just follow by this. One more term that really important in our CE field is the endurance limits. So what is endurance limit? Endurance limit is going to be the point that the sample is not going to fail under fatigue. Okay, it's a stress point that let our structures not to fail under fatigue. For example, endurance limit is going to be in between 0.4 to 0.5 of the ultimate stress over here. Okay, and if this 0.4 of the ultimate stress, it's about 414 megapascal as shown in these figures. If I apply the stress about 300 megapascal, this material is never failed by the fatigue test. But if I increase it to 500, of course it's going to fail when it reaches the cycle of around almost a million times, and it's going to fail by fatigue. And if I apply 700 megapascal of the stress, it's going to fail at about almost half of the 100,000 of the circle of failures. Okay, this is how we consider it. So the endurance limit is the stress level for infinite cycle without failures. I said easily. And we have another one is going to be the calculation part. So this one, I think you guys may be able to do it. So this one is just force over area, and the answer is 200. So you can just try to calculate by yourself. We have another one is 50. length and the deformation under the force. So to get the strain of it is going to be zero point 0.4 divided by 200, and the answer is going to be 0.002. And if the stress in linear elastic equals to 200 megapascal and have the strain of 0.001, the modulus of elasticity in the according to the Hooke's law is going to be stress over strain, and the answer is going to be 200 megapascal, 200,000 megapascal. And if the timber is subjected under the single shear, it's going to be 10,000 Newton divided by the area of 2,000 square millimeters. So the answer is supposed to be 5 megapascal. And for the double shears question, you need to divide by the two area, which means you're going to use 40 kilonewton divided by 2 multiplied by the area of 100 square millimeters. And the answer is supposed to be 200 megapascal. And for the torque that we would like to find the maximum shear over here, we can just calculate it easily by using TR over J. J is the polar moment of inertia, and we're going to get it equal to 1 megapascal. And to reduce the, okay, over here, in order to reduce the stress, to reduce the angle of the twist, we can just increase the cross-sectional area in order to increase the divider of polar moment of inertia, and then the angle of twist is going to reduce. And for the fatigue, if you would like to find the mean stress or the average stress, is going to be equal to max plus mean. So in this example, it's going to be 10 minus 2 divided by 2, going to be 4. It's going to be 4. For the amplitude, sigma A is going to be max minus min, so minus minus plus 12 divided by 2, going to be 6. And the maximum flexural stress can be calculated by MC over I, and then if we substitute everything in, it's going to be equal to 10 megapascal. And if we would like to find the maximum moment from question 59, it's just PL over 4 for the 3-point loading. And lastly, it's going to be the shear strain. And if we have the radius, angle twist divided by L, and then we're going to get it equal to 0.002 for the question 60. And then we finish the chapter number 5. According to the TAS for hot rolled steel, we normally divide the steel into two different types. The first one is going to be the hot rolled structural steel. They're going to follow the TAS 1227, and another one is cold form steel. They're going to follow the TAS 1228. So this one, we're going to select the first one. And the steel is an alloy of iron, which combined with the carbon. Okay, to see this, we can just scroll down into here. Okay, you can see that the ductility of the steel, it depends on the percentage of the carbon that we put into the alloy of the iron. Okay, so the more that we put carbon inside the iron, the strength and hardness are going to increase, but the ductility is going to decrease. Okay. So this is the node. And how does increasing carbon content in steel affect the mechanical property? So we just talk about this. When it has higher percentage of the carbon content, going to produce a higher strength, hardness, but lower ductilities. For example, like for the rough steel over here, it has just only 0.1% of the carbon content. And normally they use it for the tie rod. Tie rod is the one that we tie the reinforcement, okay, which require a lot of flexibility of bending. So that's why we put just only 0.1% of the carbon to get the strength out of the carbon. And the steel is going to, the iron is going to provide the ability to be flexible, in order to bend it. And for the question 64, the stainless steel contain 10% of which element? So it's contain 10% of chromium, which is a really expensive oxide. So that's why you rarely see the structures use this stainless steel. Okay, because it's going to cause your structure to be really expensive. But if you can, your structure is going to be really good at resisting the corrosion or really good in resisting the environmental. Uh, it's really good for environmental resistance compared to other steel. Okay. Next one is going to be the question of what are the key properties of cast iron? The key property of the cast iron, this one is general that we already discussed. The cast iron has high pressure strain and high hardness but low in tensile strength with its behavior as the brittle material. And how does the strain hardening affect the steel after bending? In cold form steel, we need to bend the material into shape. After we bend material into shape, the material is going to lose the ability to bend, which means it's going to, for strain hardening in question 66, it's going to produce the strain permanent, which means we're going to use the hot rolled steel to press it in order to make a cold form steel. And then that cold form steel is going to create the permanent strain to the material. And that material is going to have two remarkable points that we need to always think about it is it's going to have a really a higher yielding strength compared to the hot rolled steel, but according to its property that it produces the permanent strain, which means it has lower ductilities compared to the hot rolled steel right now. And when if we form the shape as the cold form steel few more time, it change its behavior from the ductile material to become a brittle material. And next one, it's going to be also this one, just higher in gear stress, but more in brittle, so in short. And RB is going to be the round bar, and the surface of the deformed bar, let's go here. So here's the deformed bar, it's going to have some ribs on top of the surface over here. So it ribs at the angle larger or equal to 45 degree to the axis and not larger than 70 degree. Okay. And under one, in a steel bar retention test, the action of the fractures occurs outside of the length. I think I have the example here. Normally, when we test for the tensile test, you can see that our sample, we're going to mark 3 points over here. 1, 2, 3. And the 3 points supposed to be in the gate length. And the gate length supposed to be 5 times of the diameters over here, and then the grip length is supposed to be about 5.5 times of its diameters. After that, after we grip into the sample like this, we would like to control the sample to be failed or to cut out into 2 pieces in between the gauge length. If the sample is out of the gauge length, so we need to reject or discard the result out from question number 69. Okay. And another point, just only the SS400 that we already discussed at the first, which means it has the ultimate strength about 400 megapascal, and then for the yield stress, it's going to be 235 for the material that has the thickness larger than, I think this one is supposed to be 245 when the thickness is less than 16 millimeters. Okay, so for 235 is for the thickness that larger than 16 millimeters. So the correct answer is going to be 245. Sorry, over here. And the next question is going to ask, Uh, what is the design stress from SS400? The design stress or the sigma allow is going to be the yielding stress over factor of safety. Okay, the allowable stress is not from the ultimate stress 400 over here, but we're going to use the yielding stress to divide with the factor of safety of 2, which means if we know that the yielding stress is 245 from the grade SS400, this is divided by 2 according to the question, and then we're going to get the answer of 122.5, the correct answer. Next, why do structural steel section with a factor of safety equal to 2 rarely fail from the fatigue? Because of what? Because of normally the endurance limit over here is going to be the point that divide if the stress is larger than endurance limit, it's going to fail by the fatigue. Okay, but if the stress of our sample is less than endurance limit, so it's not going to fail by the fatigue, which means endurance limit is the stress that in between 40 to 50% of the ultimate stress. And then we check it here. If it's 40% of the ultimate stress of the steel grade of SS400, which means it has the ultimate stress of 400 ULT, ultimate stress of 400. So 0.4 multiplied with 400 is going to get the endurance limit at 160 megapascal. But for the allowable, stress allowable or stress design, we're going to use the yielding stress, sigma yielding, divided with the factor of safety. So according to the SS400, the yielding stress is equal to 245, and if we divide this by 2, we're going to get it equal to 122.5, which means our endurance limit over here is 160, but our allowable stress equal to 1225.5. This indicates that our structural steel that use the factor of safety equal to 2, it's never gonna fail, it's not gonna fail by fatigue because endurance limit is equal to 160, but our structural steel that we use is going to be just only 122.5 in the design. So just click allowable stress less than endurance limit, and that's it. So these are many type of the material. This one is from TAS. This one is the one that we just discussed about the grade of the steel. And what else? So this one is another mark that I told in the class that you may need to remember, the percentage elongation from here. And another part is going to be the reinforcement steel. According to the mechanical property of the concrete, we know that concrete is going to be bad in tension. Okay, concrete is going to be bad in tension, but going to be good in compression. So engineers, they reinforce the steel into the concrete in order to have the tension. So reinforced concrete is going to be the term of combining between concrete and the steel together in order to have resisting the tensile force in the concrete, in order to reduce the creep and prevent a crack in the concrete. In the reinforcement steel, we have just only a few things to consider when buying it. It's just only to check the symbol. RB is from the round bar, and 25 is the diameter in millimeters. In the middle is the trademark, and at the end is going to be the steel grade of the round bar at 24 SR24, which indicate that the yielding strength is equal to 2400 KSC. And for the deform bar, most of the time we indicate similarly dB, which means deform bar. 12 mean the diameters in millimeters, and we have the trademark in the middle, and then we change from SR to SD because it's deform bar. Standard grade of the deform bar. 40 number at the back means its yielding stress equal to 4000 KSC. And we have another test. We call it um, bend test. For the bend test, it's just to examine that the ability of this reinforcement steel that can be bent 180 degree or not. In order to examine that when we bend the steel during working and it has no defects at the middle. Okay, so the steel still in the perfect condition without damaging it. So if we bend it 180 degree already and there's no defects on the sample, so this one is a good material. Okay, and this one is going to be the method how we find the diameters of the deform bar, because using vernier caliper is really hard to get the diameters because it has the ribs, which sometimes if we measure 3 times, maybe we cannot get exactly the same area for all of the 3 times. So that's why we control it by using the unit weight. And then when we would like to find the D average over here, we're going to measure the length of the sample, and then we measure the weight of the sample, and then we just plug in into this equation. We're going to get the approximate diameters of the deform bar or the round bar. This one is the bend test. This one is the one that we discussed. The range of the rib is in between 45 to 70. And this one is the deform bar, 25. And in the middle is the trademark and symbol of the grade. You can see that when it is the deform bar, they change it from SR to SD, which indicate that this is the deform bar. Grade over here, which means sigma y equal to 3000. Okay, it's not 4000 as what I show. Okay, I wrote it here. And move on to other properties. Okay. Concrete is going to be the material that going to combine between cement, water, coarse aggregate or sand, coarse aggregate, and fine aggregate. Coarse aggregate we just like commonly call it as stone, and for the fine aggregate we commonly use the sand as the fine aggregate. So when we combine everything together, just add some water in it and then combine it. Concrete is going to be the most used material nowadays. By concrete normally construct into 2 ways. One is cast in place, another one is precast. Cast in place means we're going to mix the concrete and then order it to the site and then we cast it at the site. But for the precast, which means we're going to produce it first and then we're going to place it later at the field without casting it. So we can just use that element immediately. But for cast in place, it's going to take some time and it needs a lot of preparation in order to cast it at the place. Okay. So concrete is the material that combine between cement, sand, stone, and waters. Or sometimes we need to add something called admixtures, because you guys are learning concrete technology, so it's really easy to explain for you guys. For the crushed stone, in concrete technology, we call it as the coarse aggregate, and for the sand in concrete technology, we call it as the fine aggregate. A good coarse aggregate is supposed to have the shape of the granular without sphere shape or round in each angle. For the granular shape of the coarse aggregate, it's going to provide a really good adhesion or a really good interlocking between mortars and coarse aggregate. So if you mix it or you buy the coarse aggregate, you need to observe the shape of it too. Okay. When we combine it together, we're going to form concrete. And the concrete, to get hardened, it needs to pass a process called hydration process. What is hydration process? Hydration process is the chemical reaction between cements and waters. And then it provides some heat and it changes its behavior from liquidy to a hardened state. Talking about cements that we use in our mixings. For the cement, we have five types of cement. The first one, if we build a house in Kora, we can use the type 1. It's a general one. Type 2 is going to be a little bit better than type 1, but mm, normally we use type 1. And if you would like to get it as a sulfate resistant, we're going to use type 5 instead of type 2. Okay. Type 3 is going to be the one that we would like to remove the formwork early, and we would like to get a really early high strength. So we can just use type 3. And for type 4, it's going to be the low heat cement that going to be suitable for the mat foundation or big structures to avoid cracking. And last one is going to be the sulfate resistant at the sea area or at the coastal area. It's going to provide a really high resistance to the sulfate. Therefore, question number 74, the hardened phase in concrete, we call it hydration process. And the cement type that should be used for rapid hardening is going to be type number 3. 26, effects of water to cement ratio in compressive strength. So the effects of water, sorry, the effects of waters to the concrete is going to be the strength, which means if you look at here, water to cement ratio by mass at 28 day, when we add water in the ratio of 0.7 to the cement, it's going to produce just only 23 megapascal. But when we reduce the waters to the ratio just only 0.4, it's going to provide 42 megapascal, which is almost twice better than 0.7 over here, which means the effects of water to cement ratio is going to affect by adding more waters, or we call it as the higher ratio. It's going to provide lower strength. But if you provide lower water, it's going to produce a really high strength. Okay, so both are in contrast. Okay. High water is low strength, low water high strength. Okay. Go back to here. All right, and then for the question number 77, we're going to talk on the curing procedures. In concrete, we need to make sure that it's going to continue the hydration process. To make sure that the hydration process is continued, we need to cure the concrete sample after casting it, after it hardened. For example, if at the field, if you're in the lab, after you cast the cylindrical sample, after that you put it into the water immediately. That one we call it water curing. But at the field, we cannot like cure it like that. In the field, we need to find some mat over here or some clothes, and then we spray the water on top of the surface in order to prevent the waters on top of the surface of the concrete to evaporate out. So if the water on the surface evaporate out, which means it's going to slower the hydration process, and it's going to not meet the strength that we designed or we require. So that's why we need a curing in the concrete. So we just cure to prevent the evaporation and to ensure the continuous hydration. The concrete covering for the column in coastal area is supposed to be at about 75 millimeters in order to provide the where's the image? In order to have the barrier or the gap or the covering big enough to prevent. We use the cement type 5, but still not enough. We need to also increase the covering length to 75 millimeters. Yeah, over here. Right. So why do concrete cylinders fail in a cone shape under compression? Because of the friction. This one is the one that we already talked in the previous chapters. It because of the friction at the loading head inhibits cracking at the end. So that's why I transfer the force into the middle of it. And what is the disadvantage of using concrete in the construction? This one just only one point that I would like to mention is just only the time dependent, which means shrinkage and creep can be some time, but luckily we have a reinforcement to have it. Or creep and shrinkage maybe not that usually happen. Yeah. And if we combine the compressive strength, sorry, if we would like to compare the compressive strength to the tensile strength, these two material, if we compare the compressive strength to the tensile strength of the concrete, the tensile strength provides just only around 8 to 15 percentage, known as 15 to 80 percentage of the FC prime. But actually, normally we just like assume it as the round number equal to 10%, approximate 10% of the FC prime. So for the tensile stress of the concrete, it can resist just only 10% compared to the compressive strength. So at this point, I pick 8 to 15. And for the mechanical property of the concrete, you can see that when we test it, this one behave as the ductile material, even though the concrete is brittle, right? But when we plot a section curve of it, it's going to behave similar to the ductile material. But the important point of this is, if you remember it, steel, whatever percentage you put for the carbon contents in the iron, so it's going to produce the same Young modulus of elasticity for the cast iron. But for the steel, it's different. When you put less water content, which means you're going to get a really high strength of the concrete. When you obtain such a high strength of the concrete, which means your modulus of elasticity is also high. And if in the examination, I'm going to ask you to find the modulus of elasticity of the concrete, and I provide you this curve, you must be able to find it by just pulling a linear line straight on the curve over here and then pick a point in the linear zone using Hooke's law to find the Young modulus of elasticity using stress over strain for the concrete. So this one, I think we can skip it. We talk a lot about the concrete, so I like to skip it. And this one I already mentioned. Let's move to timbers. Okay. Let's move to timbers. In timbers, we need to note on the material itself. If we cut the section, we have many parts or many layers of the timber, such as bark, cambium layers, sapwood layers, hardwood layers. Annual rings is the one that we use to indicate the age of the timbers or the trees, and we have medullary ray here. But in the structural field, we're going to consider just only sapwood and hardwood, which are the part that we use as the main layer for the structural metric. And if you would like to see the deflection, we have a lot of deflection, or we have, if you look at the defects of the timbers, we divide the defect into 7 main defects, such as bow, croak, twist, cup, check, shake, and wane. So for the check, basically it says the defects across the annual rings, okay, according to the dryness of the timbers. And the shake is going to be the crack in the annual ring like this. And wane, lastly, is going to be the defects on the timber due to timber cutting at the edge like this. But the order is just as normal bending in curve, such as bow in this direction, croak in another direction, and twist is going to be one edge lift up like this. We call it twist. For timber, it's going to be an autotropics material, which three of its axes provide three different mechanical properties. If you press the concrete in this side, it's going to provide another mechanical property. If you press the concrete in this side, you're going to get another mechanical property. And if you press the concrete in radial axis, you're going to get another difference in mechanical properties. And if we look at its behaviors according to its grain, for example, if we observe the stress curve parallel to the timber grain, you can see that it's going to behave as a brittle material similar to the cast iron. And if we observe the behavior of the perpendicular to the timber grain, it's going to behave similar to aluminum, which behave as the ductile material. Okay, so please differentiate it. And let me skip here. This one we discussed already from chapter 5, which tensile strength is going to be the highest one. The second rank is going to be compressive strength, and last one is going to be the shear strength. And if you pull the timbers in perpendicular to the grain, you can see that it's going to provide the strength about like 0.1 compared to the one in parallel to the grain. So if you test in parallel to the grain, the volume is going to be approximately 10 times better than the parallel to the grain. But for the compression, it's going to different about 3 to 4 times, which parallel to the grain is going to provide the better one, about 3 times better than perpendicular to the grain. You can see that we have a long span timbers and another one is a short span timbers. These two span is going to provide a different failure mechanism. For example, the long span is going to provide either compressions failures or tension failures at the bottom. But for the timber that has the span to depth ratio less than 10, it's going to fail by the horizontal shear, which means this one is going to fail at the neutral axis, the NA axis. Okay, but for the one that has this span to depth ratio larger than 10, this one is going to fail in either compressive or tensile force parallel to the grain. Okay, I'm gonna skip this. And then we're going to answer the questions. So question 82, timber is an autotropic material, which means it's going to provide different properties in three different axes. And for the longitudinal wood crack crossing the annual ring due to the uneven drying, is going to be checked. And the suction curve of the wood loaded parallel to the grain is similar to the brittle material. And for the one that perpendicular to the grain is going to be, for the tensile strength, it's going to be 10 times less than parallel to the grain. So it 1 by 10. 86 compressive force applied to perpendicular to the wood fiber result in gradual crushing. Okay, the one that perpendicular to the grain. And why still concrete used more than wood for modern house? Simple question, because of the deforestation and the high price of the wood and a really high price of maintenance. According to the TIS 107, HS41 of the hollow steel supposed to have the percentage elongation about 23% of it. And that's it. If we look at the brick, there are a few nodes that I would like to mention. For example, the first one is going to be solid brick and the hollow brick. To differentiate it, just only the resistant area of the solid brick, we identify it by when the resistant area is larger than 75%, and the hollow brick is going to be larger than in between 40 to 75%. Second is sand. 3 is water or and add with Portland cement. Normally we add these four together. silica cement, sand, and waters, and also Portland cement. But in Thailand, normally we not gonna use Portland cement. So from this slide, I can divide this into two questions. What are the modal bind Mansory unit together? It's constituent of silica cement, sand, waters, Portland cement, or I may ask in Thailand, you may need to answer just only silica, cement, sand, and water. It's just only three. But for the normal one, we have four contents. But for Thailand usage, we're going to have just only three contents. What else? If you look at the good side and the bad side of the brick, just by weight two structures, which means we increase the dead load in the structures if we use the solid brick system compared to other material. Combination between coppers and magnesium, and we call it non-porous material. It light, it high strength, identified as the high corrosion resistant material. That's why, which means it's going to be also good at corrosion resistant compared to other material. That's why you can see that most of the time they place it outside of the building when it's in contact with weathering, so it's going to be okay compared to other material. This is a sample from Hong Kong buildings. We talked about this already. It's really good for waterproofing, corrosion resistant, and good for the UV resistant. And it's going to have a really small damage to it, like in a really long term. So we can save a lot of the servicing cost. But the bad thing about the aluminum is just only the modulus of elasticity that has just only approximately 70 gigapascal. That is really low compared to the steel, about like 3 times less than steel. So for the long span usage of this material, is going to provide a real defect compared to other material. For the FRP, okay, let me answer this question first. This one is 23, we just talked about it. How are pre-stressed concrete piles typically installed? It's supposed to be installed by pile driver. And then we have 90. Why is ready-mix concrete highly popular? Because we can control the quality and then it's really convenient to others. Significant advantage of using brick in masonry, just only weathering resistant. And the main problem of using clay brick in structural, it's flammable. It's the main problem of using it is just only the heavy dead load. Brick load resisting behavior most similar to concrete in what way? So it's supposed to be good compression, low tensile, but considered as a brittle material. For question 94, clear advantage of aluminum over steel, just only lighter and rust resistant. And for the disadvantage of aluminum for load bearing structures, I think I already explained by here, because of its low modulus of elasticity, which provide a really high deflection to the structures. So in terms of using as the structural element, it's not really a good one to use it, but for just like the decoration or the environmental resistant, or resist only a small load as glass and put it outside, it's going to be a really good material to use it. And aluminum via the steel regarding to the temperatures, of course, for fiber reinforced plastic composite or FRP composite, it's a really lightweight material that can hold a really large tensile force compared to the steel. And its component consists of the continuous strand mat at the middle, and then we have 2 layers of the fibers, top and bottom, and then we cover it with the strand mat on top, and then the surface wheel over here. It's used a lot in maintenance or maybe to reinforce for the extra resistant force. For example, in this pier, column pier of the bridge, we add the FRP composite in order to strengthen it from outside. And then this one is to prevent cracking from the bottom of the flat slab. And sometimes if there's some crack, they just like use FRP to repair it if it is not that really big deal. The FRP is a brittle material which when we going to fail immediately after it reach its maximum point. And this one is for the ductile material or DM. For ductile material, it's going to curve like this, like similar to concrete. You're going to curve like this, go up and go down. But for the FRP, it's going to behave linearly like this. After that, it's going to fail. It can reach up to 1,500 megapascal in tensile. Compared to the steel, it can goes up to. The interesting things about this material is its modulus of elasticity. So it's about 1/3 of glass fibers and about equally in numbers compared to the structural steel. But if we compare with aluminum, you can see that aluminum is about like 3 times less than the structural steel. But the FRP composite, it's almost similar for the modulus of elasticity. This is its material, and this is some standard. It's a brittle material, linear elastic to behaviors, and abrupt mode of failure immediately fail. Yeah. And these are the comparison table. Okay, then let's move on to the question. Starting with question 97. The superior features of GFRP over the steel, of course, it's going to be fiber is not a corrode material, which means it's non-corrosive and non-electromagnetic. So this one is the what we call a beneficial part. And the main disadvantage failure of GFRP is the brittle failures according to linear resistant force. And precaution of using GFRP outdoor is it's not really good at UV resistant. In some time, the surface of the FRP can be degraded. Question 100. Strength to weight ratio of the material. Of course, GFRP is going to provide a really high strength to weight ratio. And next is for the concrete block. Okay, so let me move to here. So concrete block basically is the material that combine between cement, water, and fine crushed stone. And if you look at here for the concrete block with the grade of A1 and A2, let me change this. This one's supposed to be A1 and A2. For A1 and A2 over here, it's a grade that really good for using I think it's over here. It's really good for use for everywhere. You know, you can use it for above the ground, under the ground without a surface protection. And if you look at another material that we call it as the solid precast, another material called reinforced, another precast material is the solid precast pre-stressed slab. The reinforcement that we use it, we call it the high strength PC wire. 103 purpose of using bentonite slurry in a light diameter bore pile. If we move to here, you can see that we use bentonite slurry in order to prevent from prevent the failure of the hole. Okay, for example, for the sand layers, sand layer is not going to stick together compared to the clay layer. That's why when we create a borehole like this, there are a lot of chance of sand going to fall out from its layer to the bottom, and then we don't want it to happen. That's why we need to use the bentonite slurry in order to inject the slurry or the clay inside the sand layer to maintain the borehole, which means we need to stabilize the borehole. And then for the question 104, advance of span pile over regular driven pile, it's just only the dense concrete. It's really stiff, really hardened, and really good at resistant force. And for the first class concrete pipe installation, if we slide down to the concrete pipe, we have over here is the first class above the top by using sand. Okay. And the main ingredient of the concrete block is going to be concrete. This one going to be. This is going to be cement plus water plus crushed fine crushed fine stone. Okay. And the ratio of grading it's in between 1.4 to 1.8. And how does a hollow core slab differ? So what is the difference of the hollow core slab compared to the solid slab? It's just only hollow core slab. It can expand the span up to 12 meters without bracing. And two main concrete pipe joint type are these two, tongue and groove, with the bed and fiber. Like this, just pick this one. And the test that often show localized shearing and buckling is supposed to be the bending. Okay, and these are not really that important, so I'm gonna skip this. And for the question 113 is going to go back to chapter 6.1. The Poland cement type of the mass concrete suggests that we need to use the low heat concrete one because we would like to prevent it from the cracking caused by the heat. So that's why we need to use the low heat concrete in order to make the continuous construction process. And 14, this one is not important, but this one is E10. And the pitch pocket is also not important. For a concrete block, if we go back, for a concrete block, we have four sizes of 70, 90, 140, and 190. So we have four sizes. And typical PC wires count in the solid precast slab. It's supposed to be in between 4 to 7. If you look at why it's 4 to 7 is here. So normally it's 4 to 7, but in this company catalog starting from 5. Okay, but normally it can be starting from 4 to 7 over here. This one I would like to skip it. And I think that's about it for our review. And for the other extra things that you would like to know, you can just go back to the previous video from chapter 5, 6.1 and 6.2. And then you can just learn from it, like all of these contents. All right, so good luck for your final exam.